All right, we are live, everyone. Hello, happy Tuesday. My name's Gina Varamo. I'm the outreach manager for NOVA, and I'll be your host this afternoon for a very special virtual field trip to the Corning Museum of Glass. This is the second field trip inspired by our newest chemistry series, Beyond the Elements, a three-part look into the fascinating chemistry that makes our world and everything in it. So during our last field trip, we focused on the DNA and the chemicals responsible for making life. But today, we're going to turn up the heat to about 2000 degrees Fahrenheit as we dive into the world of glass. So glass blowing personally is something that I've always been interested in and I've wanted to try. So I'm geeking out right now and I'm really excited to talk with our guests today. So most of us interact with glass every day, from looking out our windows, working on our screens, to getting a drink of water, or baking a casserole, anything. But what's it made of, and how does it get its strength? So today we're going to find out with our special guests, Eric Meek and Chris Rochelle, and the Corning Museum of Glass. So the Corning Museum of Glass is a nonprofit museum dedicated to exploring just glass. Annually, they welcome just under 500,000 visitors from around the world, and the museum's campus is home to the world's most comprehensive collection of glass, the world's foremost library on glass, and one of the top glassworking schools in the world. You may or may not have seen them on Blown Away on Netflix if you've been binge watching some TV like I have over the pandemic. And we're thrilled to have Eric and Chris joining us today for some live demonstrations at the museum. So if you have any questions while they're doing their thing, please feel free to drop them in the Q&A section if you're joining us via Zoom, or in the comments on Facebook and YouTube. We are watching them all. So if you have any comments, questions, feel free to drop them in, and we're going to get to as many as we can during our time together. So without further ado, Chris, Eric, I'm going to pass it off to you.
Hey there. Hey, everybody. Thank you so much for tuning in. We're really excited to be part of this partnership with NOVA. We're so happy with how they represented this material we love on their Elements series. So we're going to give you all a little bit of a deeper dive into what goes into making glass and the different things that you can do with it. Now, we talked about chemistry. We're going to touch on chemistry a little bit, but we're also going to focus on the physical properties of the material that make it so versatile, that allow us to use glass in so many different ways. So as I was introduced, my name is Eric Meek. I'm a glass blower and I'm a program manager here at the Corning Museum of Glass. The glassmaker working with us today is Chris Rochelle. Chris is a veteran of glassmaking. He's been doing this a very long time and has a great presentation lined up for you today. Also joining us is Catherine Aguilar. She's our science educator here at the museum. So hopefully between the three of us, we should be able to cover any questions that you throw at us. So again, we're really excited to share what we know and love about glass with you all. I'm going to get started just with a quick tour of our shop. So here on this side of the stage, we have a glass melting furnace. So this is a 2,100 degree furnace, and there's literally a vat of molten glass in the bottom of it. There's a crucible that contains about 200 pounds of glass when this is full, and it's kept at 2,000 degrees 24 hours a day. This one is heated with electric elements, so it's a nice efficient furnace, and this is where everything that we make gets started. We have a selection of blowpipes here and gathering irons that we call punties that we use to collect the glass out of the tank, and you'll see us do that in a little bit. On down on this side of the stage, you'll see our master glassmaker, Chris, reheating the glass in this reheating furnace. So as we're working with the glass, it cools down, and when it cools, it becomes rigid. So we continually have to reheat it to keep it hot enough to work. And then the final stop for a lot of the things that we make is this, a 900 degree cooling oven where the glass cools slowly overnight. Glass has to cool down very gradually to prevent it from cracking and breaking. And you can see some of the examples of pieces that we made up here on this annealer. This is a beautiful chalice that Chris made with a lovely intricate air twist stem in it. So this is an example of the kind of things that we can make with our creativity.
We just had a brief audio and visual freeze there. So we'll give a little time. Hopefully things will come back together. in the meantime, I see that we've got folks. Yep, we're on it. You know what's the fun thing about live events, y'all? Sometimes the audio and the video freezes, and that's all right. You know, we're all still learning how to do this in this pandemic time. But in the meantime, please, you know, put in your questions, put in any other comments you have. We will work on this audio and video as it's going on. So please be patient and bear with us. So in the meantime, if you haven't already, I highly recommend checking out Beyond the Elements. So Beyond the Elements, like I mentioned earlier, is our new 3-part series based all about the world of chemistry. It's hosted by David Pogue. So for all of our fans out there that loved hunting the elements or making stuff or Nova Science Now, David Pogue is back to join us in a series all about chemistry. So in each episode, he explores a different piece of chemistry. Episode 1, we take a look at reactions. So the chemistry that makes explosions. We talk about the Haber-Bosch, where it makes fertilizer, but can also be an incredible explosive. We have Beyond the Elements Indestructible, where we're talking about a whole bunch of different materials. So we will be talking about things like rubber, glass, what keeps tires on the road when NASCARs just are like flying at the speed of, you know, not the speed of sound, but when they're going really fast. And then in our last session, we're talking about Beyond the Elements life. So we're really taking a look at DNA. So what makes our bodies, the chemicals that make our bodies up and how we are the way we are. So you may have joined us last time for our virtual field trip with Dr. Monica Hall Porter, where we extracted DNA from strawberries. And this is our second field trip where we're look at the Corning Museum of Glass, and we'll have one in the future looking a bit more at reactions. So in the meantime, I highly encourage you to visit Nova's website and take a look at those episodes. We also have a cool interactive Beyond the Elements reactions where you can take a deep dive into some of the most popular reactions that are happening in our world: photosynthesis, Haber-Bosch, fire, and you can build the different chemicals and reactions and learn a little bit more about them. For all of our educators out there, they comes with a free lesson plan and educator guide, as well as some teaching tips and discussion questions that make it really easy to plug and play into your classroom. And you can find all that information on Nova's website or on PBS Learning Media if you look for the Beyond the Elements collection. So with that, let's check in with our
folks. This is Chris.
Can
you hear me? So we just lost all of our internet here at the museum. I just logged in with the cellular network. So I don't know if we have a way to get the video to you, but you can hear me and I can hear you now because I'm using cell service.
Yes, we can definitely hear you. Oh,
looks like Eric just joined.
Oh gosh, live events, man. This is what happens. Thank you everyone for being patient and sticking with us.
Hey, Gina, we're back. Can you hear me?
I can hear you.
You know what? I'm going to do this the old-fashioned way and use my phone, okay?
That sounds great. I think Chris just needs to mute himself so there's no feedback.
Okay, I'll mute myself and then we can hear Chris's audio, okay?
Okay.
Look at my camera. There we go. Okay.
All right, we see you.
All right, Chris, just a sound check. Everybody hear me okay?
We can hear you.
Okay, very good. Sorry about that. We're going to get right back into this. So here at the museum, we do demonstrations for our guests every single day. And a lot of those demonstrations showcase the skills
and a lot of the techniques that artists use to create an object. Many of those are vases, bowls, goblets, anything decorational. This program that we prepared for you today takes a look at some of the properties of glass. We're going to take a closer look at some of the properties of material and things that glassmakers have to learn how to work with and adapt. So we're going to jump right into it. Eric already showed you our melting furnace, and this is really where it begins every single time. Again, the temperature in here is 2,100 Fahrenheit, and our glass is sitting inside of a big ceramic crucible. So when I dip in with this solid rod, I can start to turn, and that winds the glass onto the end of the rod, almost like you were gathering honey. So this is the same consistency as table honey when it's this hot, and that's why you see glass blowers always turning. One of the most common questions we get is what happens if we stop turning, and that's exactly what happens. The glass will just run right to the floor. So that's the first thing you have to do when you start blowing glass, learn how to gather the material and control it by turning very carefully. Another wonderful property with this material is its ability to stretch. And Eric, I'll have you give me a hand with this if you can. I'll take just the tiniest little gather, and we're going to pull this into a thread. I'll have Eric use the tweezers, and this is just the size of a tiny pea, but you can see that he's pulling really slowly, and if he pulls faster, we can stretch this really far and also very, very thin. And keep in mind when you see this, fiber optic cable, which is a very special type of glass, but it's stretched so thin that it's actually bendable. And if you take a look at what Eric has in his hands, you can see that he's able to not only hold on to that because it's lost its heat instantly, but he's able to loop it around itself. So as long as glass is stretched thin enough, you can bend it quite a bit. And that's really why fiber optics is possible. And speaking of that, we just passed the 50th anniversary of the technology used to create fiber optics. So that's a little fun with dripping and stretching glass. What we're going to show you next is a bubble. So I'll gather up some material on the end of a blowpipe. Now, for 2,000 years, people have been gathering glass on pipes, shaping it, and using their own breath to inflate it. Well, currently, with COVID running around right now, we can't actually do that. That's why we're wearing masks. But we have an auto inflation tool that you'll see me use here. I'll latch this cap onto the back of the blowpipe. I want to shake this up a little bit and get it under control first. I'm using a wooden scoop called a block that's been soaked in water to do that. There's a foot pedal in front of me that I'm going to tap here in a moment to engage the air pressure through the system. Right now, the air is regulated to about 2 psi, which is very, very small pressure. That's like a whisper. And you can see how easily that bubble comes right out. Now, if I wanted to make something like an ornament or a goblet, this is enough material to do that. And I can inflate this a little bit further. But what I'm going to do is turn the pressure all the way up to about 20 psi and just hit that foot pedal and not stop. And you can see that that bubble keeps inflating. And at this point, it's pretty much rigid because I've inflated it so thin that it just collapses under itself. It's almost as thin as cellophane. And I've got a little piece of this down here. So just like Eric was able to bend that little stringer, you can see that that little bubble that I inflated is so thin that I can actually flex it quite a bit. So I'm going to dial the pressure back down here because I next want to make a functional little item. And I don't need all this pressure. This is a really nice system that we put into place during our shutdown. And when we reopened our museum in July, we were able to continue blowing glass. But again, I only need a small amount of pressure, probably 1 to 2 psi. Okay. So we had some questions before about color use with glass. All the material in our furnace is a clear, transparent glass. It does look orange when it comes out because it's emitting a lot of light. That's the infrared that you see, 2100 Fahrenheit. But I am going to roll through something called frit, which is on our metal table here. These are little chips of crushed colored glass. They're pretty small. They're about the consistency of granulated sugar. So as I roll through with that molten gather, those little chips of glass heat up and that causes them to stick. And then I'll melt this all in. So talking about the chemistry of glass, the basic ingredient is sand, silica sand, which is a really clean type of sand. Soda ash and limestone are the other two main parts, mixed together in right proportions. melted down with this amount of heat, turn into soda lime glass. That's the most common type in the world. Colors are formed by mixing in different metallic oxides or chlorides. And this is a nice blue, we call it copper blue. But again, you see that orange because of the heat. So to make this a functional object, I already have the piece in mind. I want to do some pre-shaping before I start the bubble. Glassmakers love to use things like gravity whenever we can. So I'm going to get a little bit more heat on this. And using gravity, I want to stretch this bubble. I've left a little excess thickness in the tip of this bubble. That's a little bit hotter because it holds its heat longer with that mass. So as I start to inflate, that's the only part that really expands. And I'm going to have Eric make a little handle for me called a punty. Now, aside from the color, this represents a pretty symbolic object in the glass world, a light bulb. And actually, one point here in Corning, the very first light bulbs for Thomas Edison were created by hand. We're going to go a step further, though. We're going to turn this into a little bottle. And that requires transferring this bubble off the pipe. So Eric's forming what we call a punty that I'm going to attach to the tip of the bubble. I squeezed in a constriction here where I can break this free as soon as we have our punty attachment made. This takes a little cold shock with some steel, and you flip the bubble around. Now you can actually see there's a pretty small opening in the tip of this. And this is the transfer that we go through with almost everything we make. We have to allow the glass to turn rigid, which we tend to call cold, and that's a relative term. Cold glass to a glassmaker just means rigid. And this glass is rock solid once it hits 1,000 degrees. But it takes a little bit of time to reheat the opening. I want to turn this into basically a little cruet. So I'll soak some temperature back into this. In a moment here, I'll have Eric shape up a little bit of glass that we'll add for a handle. This is something called a Roman bottle. And talking about 2,000 years of glass blowing, the ancient Romans were the first to really figure it out. Now we have electric ovens here. We have gas-fired furnaces as well, our other shop. Obviously, back then they didn't have either of those, but they used wood fire.
So, Chris, we have a question about the blowpipes. Do they get hot?
The blowpipes do get hot, but the heat doesn't transfer all the way up because they're made from stainless steel, which is a pretty poor conductor of heat as far as metals go. And Brad, you might be able to focus on the pipe here. You can see that they all have the same kind of heat signature. Where they're shiny, that's pretty safe to touch. Where they're dark and tarnished, that's about 1,000 degrees right there. So you want to be very careful. And that's something you'll learn on the first day of glass blowing, not to grab that part, but stainless steel. So Eric's formed up just a nice little cylinder of fresh glass. I've allowed the bottle to really just stay rigid now so I can form the handle without the bottle slumping or distorting its shape. And just a nice little detail there, that little curl at the end, I like that. So when we make a piece of glass, something like this has to go through that slow cooling process. Eric pointed out our annealer, which is right behind me. So this object would need about 8 hours to slowly cool from 900 degrees down to room temperature. We're not going to do that with this one, though. We're going to get this off the punty. And we're going to set it down on the floor here, and we're going to let it cool rapidly. And we'll come back to this and see if it stays intact. But we're going to carry on with the demonstration. Actually, you can see I left it out of the oven long enough that the bottom got a little bit cold and it actually fractured and cracked. And that will probably continue to break over the next few minutes or so. But we're going to carry right along with the presentation and talk a bit about why we need to anneal glass. When glass cools, it's basically contracting. When it's heated, it expands. But that cooling process, that slow cooling process, is what eliminates any stress that would build in the glass to cause it to crack, as we've just seen with that bottle. Now, there's a way that we can show you that movement, and we're going to use our cold steel table, cold to glass, the molten glass. And I'm going to drip some glass on here and cut it off and make a tail. And Brad's going to get a good close-up shot of how the glass will move when we do this. That steel table is very useful. It's called a marver. And really the steel robs the heat from the glass so quickly. And we can use that to our advantage. So we'll stretch a nice little bit out. Now watch very closely the tail. When that fresh molten glass hits the steel, it chills the bottom layer. The top layer of glass is hot and molten still. As it starts to cool, it's wanting to shrink. It's wanting to pull in. But the bottom layer is already too rigid. It's frozen in place, so it can't move. And the result is that you get this bend and this lift in the tail. So what we're actually seeing here is the stress, the tension that's building in the glass as it's cooling at different rates from the bottom to the top. So there's not really much we can do with this tail. It's just kind of a fun little object to show you. We're going to come back to the different types of stress. I want to talk about compression and tension a little bit more. But the next step here is we're going to go to a little electrical experiment. We have our conductivity system set up over there. And I'll have Eric bring me a fresh gather in just a moment. But what we have is our power source. We have a couple leads, a metal tool. Connecting those leads creates a circuit. And that circuit carries through and we get the light bulb to engage. Now, a lot of people probably recognize this piece of glass insulator, and this is room temperature. Obviously, I'm holding on to it, rigid. When you touch those leads, you get no current. Again, metal, great conductor. We see that current, the light bulb shines, nothing with the glass. But with a molten gather, Eric's bringing over, we'll drip it right onto those leads. It takes a second for this to kind of warm them up. But once they do warm up, we can see that we have now created a circuit with glass. So why does it work with the molten glass and not the rigid? When glass is rigid, all the ions and the atoms and the molecules in it are kind of frozen in place, but they're not close enough to carry current. When you heat everything up, all those ions, electrons, and everything are really moving around so quickly that they're so agitated that they're bouncing off of each other so fast, and that helps to carry that current through. In fact, as this starts to cool and turn rigid, you'll see that that light bulb now begins to dim because those ions are starting to kind of freeze into place and they're not in position anymore to carry that current. So this is just a fun little model for electrical current through glass, but this actually has a really huge application in industry. So when you have furnaces that can melt thousands of pounds of glass to help that furnace run more efficiently, once you get it hot, you can actually run electricity through it to carry that current.
So there's a question about recycling glass. Is it possible to remelt some of these glass?
Absolutely. Glassmakers love to recycle. Now, in the case of that little bottle that I made, and you can see that the crack has actually started to kind of form up the side of the bottle a little bit. Because we put color in this, we don't want to remelt that because we only have one melting furnace and it's clear glass. So if we were to start mixing color in there, it basically contaminates it. Now, you could remelt that. It would be no problem to make something out of it again, but we want to only keep it to melting clear glass. So talking a little bit more about the stresses in glass. When glass cools quickly, we've already talked about how that creates a lot of tension and it wants to break. But we can use that quick cooling to really strengthen the material through something called compression. So we have a bucket of water here. This is just a bucket of cold water. What I'm going to do is drip some molten glass into that, and Brad's going to get as close up of a shot as he can. What you're going to see is basically something that looks like a tadpole of molten glass. And watch very closely at that drop, the fattest part of it. That water is going to cool this drop from all sides simultaneously. And what that does is creates a lot of compression. So you can see how the outside of that drop goes clear very quickly because it's cooled so fast, but the inside stays hot longer, actually stays soft longer. As that inside is cooling, it's trying to pull in, it's trying to shrink from that movement that we talked about, but it can't actually move because the outside layer has turned rigid almost instantly. So what you get, and we've made a couple of these already, I'm holding on to one. These are called Rupert's drops, Prince Rupert's drops. So the outside gets chilled and it freezes in place almost instantly. The inside, as it's trying to pull in, can't pull the surface in because it's rigid. And what that does is it pulls away from the surface, and that creates tension or tensile stress, which glass under tension is extremely weak. but the compression layer on the outside from cooling so fast creates a lot of durability. Glass under compression is very strong. So this is called the Prince Rupert's drop. And I'm just going to give you a little demonstration of the strength here. I want to wrap the bulk bit into this little napkin, and I'll use our hammer and our metal table. So this is the head of the drop. Repeatedly over and over again. I don't know if Brad can get it or not, but there's dents in the metal table from the Rupert's drop. So this is just damaging the metal, and I'm doing absolutely nothing to the glass. But Eric, do you think you could bring that case up here? Prince Rupert was a Bavarian prince who in the 17th century was sort of a Renaissance man, a jack of all trades, an inventor, an artist, and a scientist as well. And these drops are named after him because in his court, he would have his glassmakers create these. He would bring them to court, and he would place them in his guests' hands, and he would actually shock them considerably using them. So there is an Achilles heel to this drop, and it's kind of difficult for me to grab a hold of it with these gloves, but once I do. So there's a tremendous amount of compression on the surface, but all that tension on the inside. So what we need to do is pierce through to that tension. Now you notice that the tail tapers off and it gets very thin. So where it's thinner, this section cooled together simultaneously in the water, unlike the bulk of the drop. So there's not nearly as much compression strength in that thin section. So if I can get these nips around there just right, and if you take a look at it, as soon as we break through that compression, it exposes the tension, exploits it, and it's catastrophic to the drop. Now, if you want to see that again, or you want to really tune into that a little bit better with some high-speed footage, there's a lot of videos circulating on YouTube now that actually show that at very slow frame rates. You can see the fracture travel from the tail all the way through the head of the drop at a mile per second. That's the velocity, which is really mind-blowing to me. So the last little thing that we have is called the Bologna bottle. I do want to talk just a little bit more about the different types of stress in glass and show you some samples. Now, that Prince Rupert's drop is kind of oppressive because it's cooled so quickly in water, that molten glass in water. If you watch that episode, Indestructible, Eric was talking quite a bit about compression glass, tempered glass, and this is an example of that. So when tempered glass is created, you take a window that's been formed. Once that window is formed and cut to shape, it's then reheated ever so slightly in an oven, and jets of cool air hit it from both sides. And that squeezes the surface, creates compression, drives tension into the middle layer of that. So that's a little bit, it's not quite as crazy as the Rupert's drop when it breaks, but you get this breakage pattern, these tiny little cubes of glass that if this wasn't in laminate right now, you could actually run these around with your fingers and you would get cut. So that's actually what's used in the side windows of cars and automobiles. Shower glass doors are often made of that. Backboards for basketball are made from that. The other very common type of glass is just regular annealed glass, something you'd find in your home window. And you can see when it breaks, you get this really jagged edge, different size and shape pieces of glass. So this is something that would be quite hazardous in a windshield of a car unless you had two layers that were laminated together. So an acrylic laminate between the two, when this breaks in a windshield, you get the same jagged edges, but they're held in place by a laminate barrier. And that's how that's utilized. So for compression stress, this is really important for things like mobile phones and iPads or any device that you want to have a really thin screen, touch screen capability, where you can use a really thin piece of glass, but it's really strong. So it can take a lot of that, pushing on it and all that pressure and not actually break it. So that's, we talked about thermal tempering, but those thin pieces, if you're familiar with Gorilla Glass, that's actually a process called ion exchange, and that's a chemical tempering process. But the last little thing that we have here, my audio's out. We just dropped.
We can hear you. Your videos just, there we are. Now we see you, Eric.
We're back to another camera here.
Can you also hear me?
Only through my microphone.
Okay.
So I'll take over with the narration here. So Chris just introduced what we call the Bologna bottle. And the Bologna bottle is much like a Prince Rupert drop, only a little bit different in form. So rather than being a solid drop, we actually made a hollow bubble that was cooled in the air, not annealed. And because it's not annealed, it has a tremendous amount of strength on the surface. We can literally drive a nail with this. But just like that Rupert's drop, this also has a little Achilles heel. You can see there's a small opening on the top there. And Chris is going to put it down at a safe distance here. And he has a steel stylus. He's just going to tap lightly on the bottom there. And you can see that inside all of that tension and compression strength is released as soon as he just taps the bottom. So very strong on the surface and very, very delicate on the inside. So Chris, we had a couple of questions come by. I have the microphone on, so I'm probably just going to answer these. But one of the questions was about the kind of glass that we're using. So we're using a clear glass here, and this is a very common type of glass. It's called soda lime glass. So it's made up of sand, soda ash, and limestone. These are very typical, very readily available ingredients. We literally take those raw ingredients and shovel them into our furnace here to melt. There's a crucible inside of the furnace there. You can just kind of see the pot. And then you can also see the heating elements in there, just like your toaster, that melt those ingredients down to a point where they become liquid glass. Now, we also had a question in the Q&A about windows settling over time. So we're in a space here that has a glass facade. Glass has been used in architecture for millennia, for many, 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 many years. And a lot of people have heard that over time, glass, and especially old stained glass windows, can actually settle with time, that the glass, because it's similar in structure to a liquid, that it might be possible for it to settle over time. That's actually a fallacy. And Corning Incorporated is a company here in town that has a long tradition of making glass. They actually did some tests that simulated millions of years of aging and of gravity in glass. They actually found that glass does not, in fact, move over time. Glass actually has all of the physical properties of a solid, but chemically and structurally, internally, it looks like a liquid. So it's a bit of an enigmatic material in its own. So I'm going to bring up the Q&A here and see if there's anything else that we can address.
Yeah, there's a few questions. There's a few great questions in here. Is it possible to remelt the glass? Like, can you reuse it at all?
Yeah, absolutely. So is it possible to remelt the glass? Sure. So all of the scraps that you see on the floor here, we actually love to use our recycled glass, because if we take these clear glass scraps and we reintroduce them into the furnace as we're melting down the sand, these scraps actually help the sand and the raw materials melt a little bit faster. So, glass has been made for about 4,000 years now. It's been blown on the end of a pipe for about 2,000 years. So as long as people have made glass, they've recycled it, because they learned early on, especially when the fuel source for melting glass was wood, they learned early on that you needed all the help you could get to melt the glass, and putting a little bit of your scrap glass in there helped to melt the raw material. And we still do that today. Great question.
We have another question about what's the difference between a glass container that can resist heat and one that will just break when it touches a hot liquid? That's
a great question too. Now, when we say glass, we're speaking, of a very generic term. There are actually thousands and thousands of different formulas for glass. Now, we talked about the common type of glass that we use here, soda lime glass. It's the same kind of glass that you use, that you make a mayonnaise jar out of, or a window. That's all soda lime glass. But there are tweaks in the formula to give the glass different characteristics. There's a popular type of glass called borosilicate glass, which is especially heat resistant. And that means that it doesn't expand and contract. The material doesn't expand and contract as the glass heats and cools. And that means that it won't break. So soda lime glass expands and contracts quite a lot, as Chris illustrated on the table here when he spooled that dropout. You can actually see glass moving as it cooled. Now, if we did that with a borosilicate glass, which commonly is known as Pyrex, there's a brand name of borosilicate glass called Pyrex. you wouldn't have seen that same movement because it's a formula that doesn't have that same expansion, that same coefficient of expansion. And that allows you to take and bake a casserole in a Pyrex dish and take it directly from your oven and sit it on your counter without worrying about it cracking. Great question. A couple other types of glass too. Somebody I saw asked about crystal.
Yeah.
So crystal is actually glass with a very high refractive index. That means the way that light passes through the clear glass is different. So glass with a high refractive index means that a lot of the light is reflected back out when it hits a wall of the material. And that makes it, in layman's terms, it makes it sparkly. And we all love sparkly glass. But glass with a high refractive index is called crystal. So crystal can be made out of soda lime glass, but more commonly, crystal is made by adding lead oxide to the silica as it's melted down. That gives you that beautiful refraction.
We also have a couple questions from Facebook. One of them is, does the glass in the furnace have to stay permanently hot? And a very similar question is, what temperature does the furnace need to be to melt the glass?
Very good question. So the glass in our furnace, we keep it hot because if we have this furnace here and it has 200 pounds of glass in it, it's not really something that we can turn on in the morning and heat up. Here at the Corning Museum of Glass, we blow glass 362 days a year. And so that our furnace just stays on. If we were going to take a break and maybe not blow glass for a month, we would scoop all of the material out of the furnace and then shut the furnace off. But we have to make sure that all the glass is out of the furnace, because if there's glass left in there, as it cools, it will destroy the interior of the furnace. So that furnace there stays on literally year round. I think the last time we turned this furnace off was sometime in 2018. So it's been a few years back already.
Wow. We also have a couple students that want to know, why is glass so malleable when it's melted?
It's the most basic questions that have the hardest answers. The thing that allows us to shape glass is that glass doesn't immediately turn from a solid to a liquid, right? So think of a common material that in solid form and in liquid form. Across the country, we know this right now, right? Because it's February, and at least here in upstate New York, there's ice all over the roads. So water, I think we all know the temperature at which water freezes and becomes ice. It is a temperature. Like, we know exactly the temperature at which water freezes and becomes ice. Glass is different. Glass is just a different material. And rather than freezing and becoming a solid, glass transforms over a range of temperatures from a liquid state to a rigid state. And because that transformation happens over a relatively wide temperature window, it allows us to form the glass. So Chris's expertise is really in understanding the nature of the material across that range of temperatures to be able to shape it effectively. When you're first learning how to blow glass, there's a lot of things that are really difficult to do just because they're awkward. You're doing things with your right and your left hand, you're using different tools, and that's all unusual and awkward and difficult to adapt to. The thing that is most difficult to learn and takes the longest amount of time is to read the temperature of the material and to know when you need to reheat it, how long you need to reheat it, when you can shape it, when you can push it a little harder, when you need to lay off or it might crack. And that's all about understanding that softening range that glass goes through to transform from a solid to a liquid. Excellent question.
We have a couple folks that I think are interested in, how do I get started blowing glass? Like, if I wanted to start doing this, what are some good resources that I can look at? Is there anything I can do, locally, things I should be looking into? Like, what do you have for our budding glass blowers?
Well, there's all kinds of ways to get into it. I'm not going to condone this, but I can remember in high school using a torch and, just starting, or being in a chemistry class and using a burner and starting to heat some Pyrex rods. So there are little ways to get a taste of it. Certainly the majority of people who work as glass artists today have learned in college. So a lot of people who work here at the museum as professional glassmakers started when they went to college, and we usually pick up glassmaking in an art program in school. So I studied at a school in Ohio. Chris studied here in upstate New York. There are universities all over the country. If you're in high school, there are a lot of high school programs that have glassmaking now, and some private schools and some public schools. Also, pretty much any major urban area has a what we call a public access studio. So there are glass studios all over the country, and they operate by offering a space for artists to work, and then also what we call hands-on experiences. So in your town, if you're interested in literally getting your hands on molten glass, I would look for a studio and see if they have little projects that you can do. Here at the Corning Museum of Glass, we have make your own glass projects, hands-on projects where you can make a holiday ornament, or you can make a glass flower or beads. You can get a little taste of it. And then from there, the opportunities really blossom. You can take classes, weeknight classes or weekend classes. The Corning Museum of Glass is of course, an excellent resource for anyone learning how to blow glass. We have thousands of hours of content on YouTube. Of course, if you can make the trip here to Corning, you'd see that there's lots of opportunities for you to get your hands on glass and to start it. Certainly, if you're working at home, one of the most accessible ways to make glass is a process called flame working, which is a little different than what we did here, where you heat glass rods over a torch, and that's more akin to scientific glass working. So lots of avenues to get into it. And I would certainly encourage all of you to do it because it's just a fascinating material. Yeah,
well, we saw Chris just like bang out those bottles in like, 5 minutes. If you were, how long does it normally take to make something?
I always tell people that glass is it's like a song. If you know a song, it has to be played at a certain tempo to sound right. And while Chris is a very efficient worker, it kind of doesn't matter, where you are on your path to learning. Glass sort of determines the tempo. So you really got to keep up with the material. That being said, if you're just starting out, of course, it'll take a little bit longer because you let the glass get a little bit colder, because then it's not moving so much and it's easier to handle, but then it's colder, so you have to heat it longer. And then in terms of learning, Chris has been blowing glass for nearly 25 years, so he has a lot of experience. But if you go into a studio to learn how to make glass, you can expect to make something, after your first day. You can come out of there with a nice little juice glass, or, something to put your toothbrushes in, maybe something that you and your mother will really love. It might be a little lumpy and crooked, but hey, it's a place to start. And, that's where we all started, just with the, little objects that weren't elegant. But, the process and the material is so fascinating, it drives you to keep on going and to learn more.
That's awesome. We have a couple other questions about like, where are the elements? So your elements that you're using to make the glass, do you just heat them up and that's what makes the glass? And where do you get those elements from?
Yeah, it's as simple as that. It's kind of mind-boggling to think that all of the glass around us, from I'm looking at an iPad here. The glass on the screen of my iPad started out as sand. It starts out as silica. Like, the most humble ingredient, the most abundant mineral in the crust of the earth is what makes glass. And it's really just a process of heating it to a point where it becomes a liquid. And of course, adding the other trace elements that give it the properties that you want it to have. For example, Chris used some of this blue colored glass. So in addition to the silica sand, if we add a little bit of copper to it, we'll get a nice, what we call copper blue or aqua blue. So it's literally a matter of mixing these ingredients together, just like you're whipping up a cake and throwing it in the furnace back there and letting it melt down. And the next day you come in and you have molten glass. Not quite that simple, but pretty much.
Pretty much. We have, oh yeah, so something I learned from watching Blown Away, which I never thought about, was about the environmental impacts of glass blowing. So I'd love to talk about that a little bit more. And it also comes with a question we have of, does it cost more to recycle glass than to make it from scratch? And what is the environmental impact of glass blowing?
I talked a little bit earlier about the benefit of adding recycled glass to the raw material as it's melting down to get it to melt quicker and at a lower temperature. So there certainly is a cost benefit to recycling glass. Of course, there's a cost invested in obtaining that recycled glass. If you think on an industrial scale, if a factory is making bottles, they have to obtain all of those bottles from somewhere, and there's a cost and an environmental impact associated with that. But it obviously, I mean, the economics must work out because companies go to the trouble of doing it. I think in terms of making glass by hand like this, there's no way to mince words and say that this is not the most efficient way to produce glass. I think overall the environmental impact of making glass is relatively low because in industrial processes, glass is made incredibly fast. Like the machine which makes bottles like you would drink out of can make hundreds of bottles a minute. And so if you're melting glass, the faster you can make glass out of it, the more efficient the process is going to be. And I always like to think of the benefits of glass, say, over plastic containers, in that, if glass does get into the environment, it's inert, it degrades over time, and it basically becomes the elements of the earth again. And so I think that's a huge benefit of glass. Making glass like we do by hand, very slowly in this artisanal process, it's not the most environmentally sensitive thing, but then, so it's something that our team grapples with. But then, we think of the benefits of visual art, of doing things by hand, of being creative, of introducing art into the world. And, it's a balance that we're aware of, and we try to be cognizant of. That being said, too, I've been in glassmaking for about going on 30 years now, and I've seen massive transformations in the efficiency of equipment, and certainly having an electric furnace up here adds to that efficiency. So if you can generate electricity with renewables to power a furnace like this, it makes it all better.
Awesome. Yeah. And speaking of the artistic piece, we have someone who has a question, and I'm sorry if I'm going to butcher his name wrong, but does Chihuly use the furnace like the one at Corning?
Yeah, absolutely. You can just see a little bit of green behind me. That's our Chihuly piece, one of our Chihuly pieces in the museum here, this thing called the Fern Green Tower right there. And the Dale Chihuly and the artists who work for Dale Chihuly work out of furnaces just like this. In fact, they come to Corning often, and we work with Chihuly's team often. It's the same process that Chris just showed you here.
Ooh, we have another great question that was saying, so your furnace is so hot. How did ancient folks heat sand to make glass, and how'd they get the material hot enough to make it malleable?
These are the things that keep us up at night as glassmakers.
Great question.
Great question. I wish we could get in the time machine. Nobody will ever know how glass was invented. The thing that we do know is that there were a lot of processes that required high heat longer ago than making glass. So, to smelt iron, to make bronze, to fire ceramics, you need the same sorts of temperatures. Ceramics have been fired, I think, for around 10,000 years or more. Glass has been made for about 4,000 years. You're achieving the same temperatures to fire ceramics as you are to make glass. So the technology for getting fires very hot has been around for a long time. I mean, the simple answer is we actually have melted glass in the wood-fired furnace here. You build a contained furnace and you construct it in a way that it draws in a lot of air. The key to getting any fuel to burn hot is to give it plenty of air. And the same is true for a wood-fired furnace. So we can and we have melted glass in the wood-fired furnace just like the Romans did, and it's a lot of fun.
That's so cool. Someone in a similar thing, thinking about heat, wants to know, so what happens if the glass gets hotter than 2100 degrees? And is it possible for you to overheat the glass?
We set our temperatures at our furnace's temperatures so that the melting furnace here it's basically judged by consistency, right? So it's less important to me that the furnace is at exactly 2,100 degrees. It's more important to me as an artist to be able to go in there and gather and to see the consistency of the material. So if somebody came in overnight and they turned my furnace up 20 degrees, I would know the minute I gathered that somebody has messed with my furnace, because the glass is just a little bit more watery than I'm used to. And so, we definitely are aware of the temperature of the furnace. Now, the reheating furnace, We like that to be hotter than the temperature at which we like to work the glass, because that just gives us a little extra bump of energy. So we're reheating the glass in there. That furnace usually stays around 23 or 2400 degrees. Now, if I kept a glass in there too long and it got too hot, I simply couldn't control it, and it would drip off of the end of the pipe like water. So the glass, you know, if we were to get this glass up to like 26, 2700 degrees Fahrenheit, you know, we're talking 11, 1200 degrees Celsius, it would just become like water and impossible to shape by hand.
Great. We have, which will be our last question, probably, because we're almost at 2 o'clock. Man, there are so many questions. We can't get to them all. And I'm so sorry that there are so many questions. We've had Catherine answering them on the side too. We've been asking you live. Wow. Thank you guys for being so engaged this whole time. We have a question from Facebook who wants to know, how strong can a cracked glass piece be? So for instance, if someone makes a vase that purposely has micro cracks as a decorative feature, is it possible for the glass to still be durable for everyday use? Or is that undesirable for an experienced blower despite the aesthetic appeal?
I think the question might be around something called crackle glass, where you take really hot glass and you dip it into water and it fractures the surface in a pattern. And I think as long as that's reheated, it's healed a little bit. The scientists at Corning Incorporated will tell you that any flaw in the surface of the glass really reduces its strength. So if glass is completely pure, free of scratches, it is literally more durable than steel. But as soon as microscopic imperfections are introduced into the surface of glass, it becomes brittle. And so, you know, to answer your question, yes and no. Is it safe enough to use as a decorative thing? Is it good enough? Yeah. If you ask a glass chemist or a material scientist, they will tell you that imperfections are not good in glass. You know, the Corning Incorporated creating Gorilla Glass for device screens, you know, they're hyper focused on preventing those little imperfections from being introduced into your glass, because that's literally what leads to catastrophic failure of display glass.
Awesome. Thank you so much for answering our questions. And, you know, if folks want to continue engaging with you, they want to keep learning about glass, they keep wanting to learn more about the science of glass, how can folks stay in touch with you after this session and learn more about the museum?
I would certainly encourage all of you to follow the Corning Museum of Glass on our social media, you know, Instagram, Facebook, and then we have an amazingly robust YouTube channel that has thousands of hours of content, and we do weekly live streams. So you can see Chris and the other artists who work at the museum doing different dynamic presentations every week. And the good thing about that is we also have live chat. And so, you know, if you have a lingering question and you really want it answered by one of our professional glassmakers here at the museum, check out our live streams. Again, new content every week, and we're going to keep that going through the summer. So check us out. Certainly, if you're in the area, swing by the Corning Museum of Glass. We love to share what we know about this amazing, versatile material that is all around us. We don't even know it. But I really appreciate everyone tuning in today and giving us your attention and focusing on this unique material.
Oh, thank you so much for being here. It was just so awesome to have you guys here. Thank you so much to our partners, the Corning Museum of Glass, for joining us and for hosting these incredible demonstrations this afternoon. And thank you so much for our audience for tuning in and asking all your great questions and for bearing with us through our technical issues. You stayed here, you stayed engaged. Thank you so much. These events wouldn't be possible without our partners and our audience, so we really appreciate you and your time. If you want to see more of the Corning Museum of Glass, please watch them and Beyond the Elements Indestructible to see more about the Prince Rupert's drop and other really great things exploding. It's really fun. You can watch that on Nova's website or on the PBS video app. And while you're on the Nova site, you can find Beyond the Elements chemistry resources I talked about a little earlier. So all 3 episodes of the series, the Reactions Interactive, and a collection of video resources on PBS Learning Media. So next month, we'll be back for our last field trip in this series, focusing all about chemical reactions. So make sure to follow Nova Ed ahead on Facebook and Twitter to sign up for our free newsletter to get updates on our next session. Thank you again to our partners and to our audience, and we will see you all soon for the next session. Thanks for joining us. Have a great afternoon. See you.
Thanks, everybody. Bye-bye.